In the vast, silent arena of our galaxy, there is an unspoken set of rules. Astronomers call them the laws of planetary formation. These rules dictate that if you are a small star, you can only have small planets. If you are a massive star, you get the giants. It is a cosmic hierarchy that has worked for billions of years, a predictable blueprint that allowed us to look at a sun and guess exactly what its family of planets should look like. But recently, a team of researchers pointed their instruments at a tiny, dim red dwarf star and found something that should be physically impossible. Orbiting this miniature star is a gargantuan gas giant that is so massive it defies every model of gravity and accretion we've ever built. It's like finding a massive ocean liner floating in a backyard swimming pool. According to everything we know about how the universe builds worlds, this planet simply cannot exist. And yet, there it is, spinning through the void, mocking our textbooks and forcing us to realize that the universe doesn't care about our rules. We are talking about a world that has officially broken the laws of physics as we know them, and the implications of its existence are currently sending shockwaves through the astronomical community. To understand why this discovery is so earth-shattering, we have to look at how we thought planets were made. For decades, the gold standard was a theory called core accretion. Imagine a newborn star surrounded by a swirling disk of gas and dust. Gravity starts to clump those tiny grains of dust into pebbles, then boulders, and eventually the rocky core of a planet. If that core gets big enough, specifically about 10 times the mass of Earth, its gravity becomes strong enough to start vacuuming up all the nearby hydrogen and helium gas from the disk. This is how you get gas giants like Jupiter. However, there is a catch. A tiny star, like a red dwarf, only has a tiny amount of material in its surrounding disk. There simply shouldn't be enough dust to build a 10 Earth mass core before the star's radiation blows the rest of the gas away. So, a red dwarf having a gas giant is like a bakery trying to make a 10-tier wedding cake with only a single cup of flour. It just doesn't add up. The star in question is called LHS 3154. It is a cold, low-mass M-dwarf star about 30 light-years away. It is about 9 times less massive than our Sun. According to the standard math, the most massive planet this star could possibly support would be something like a super-Earth, or maybe a small Neptune. But the planet they found, LHS 3154b, is a beast. It is 13 times more massive than Earth. While that might not sound huge compared to Jupiter, in relation to its tiny parent star, it is a monster. The mass ratio between this planet and its star is 100 times higher than the mass ratio between the Earth and the Sun. When the researchers plugged the data into their most advanced supercomputers, the models flat out refused to produce a planet like this. The computers essentially said, error, insufficient material. Yet the radial velocity data, the wobbling of the star caused by the planet's gravity, didn't lie. The planet is real, it is right there. This discovery has pulled the rug out from under the feet of planetary scientists. If core accretion can't explain it, what can? Some are now looking back at an older, more controversial theory called disk instability. In this scenario, a planet doesn't grow slowly from a core. Instead, the entire disk of gas around a star becomes unstable and collapses in on itself all at once, creating a massive planet in a geological heartbeat. But even disk instability usually requires a lot more mass than a tiny red dwarf provides. We are witnessing a crisis in cosmology. If our fundamental rules for building planets are wrong for red dwarfs, they might be wrong for everything. And since red dwarfs make up about 75% of all stars in the Milky Way, it means we might have a completely incorrect understanding of the most common type of solar system in our galaxy. But the weirdness doesn't stop with LHS 3154b. Let's talk about another impossible world, WASP 18b. This is a massive planet, 10 times the size of Jupiter, that orbits its star in less than 24 hours. It is so close to its sun that it is literally spiraling toward its eventual disappearance. But that's not the impossible part. The impossible part is its atmosphere. When the James Webb Space Telescope looked at WASP 18b, it found that the planet has a thermal inversion. Its atmosphere gets hotter as you go higher, which is strange. But more importantly, it has almost no water vapor and is filled with carbon monoxide. According to our chemical models of how high-temperature gas giants form, it should have a specific balance of elements. WASP 18b ignores that balance. It is a world made of materials that shouldn't coexist at those temperatures and pressures. It's a chemical anomaly that suggests we don't understand the cooking instructions for high-mass planets. Then we have the cotton candy planets. Imagine a planet the size of Jupiter but with the mass of only a few Earths. These are called superpuffs. They are so light and fluffy that their density is equivalent to a marshmallow. One of these, Kepler 51d, is nearly the size of Saturn but weighs almost nothing. According to the laws of physics, a planet that big should have enough gravity to compress itself into something denser, or at the very least, its star's radiation should have stripped away its light, puffy atmosphere millions of years ago. Yet these cosmic marshmallows are still there, floating in the void. Scientists have struggled to explain how they formed and, more importantly, how they survived. Some propose they are surrounded by a constant haze of high-altitude particles that trick our telescopes into thinking they are bigger than they are, but even that is a stretch. They are anomalies that suggest the timeline of planetary evolution is far more flexible and far weirder than we ever dared to imagine. But let's go even deeper into the impossible. Have you ever heard of a planet orbiting a pulsar? Pulsars are the remains of massive stars that have gone through a supernova. A supernova is one of the most violent events in the universe. An explosion so powerful it can outshine an entire galaxy. It should vaporize everything within its vicinity. Any planet orbiting a star that goes supernova should be turned into atoms in seconds. And yet, the very first exoplanets ever discovered, back in 1992, were orbiting a pulsar named PSR B 1257 plus 12. These are rocky worlds, roughly the mass of Earth, spinning around a dense magnetic neutron star that is blasting them with intense radiation. How did they get there? Did they survive the explosion? Or did they form asterisk after asterisk the star ended its life, out of the debris of the supernova? Both options seem impossible. If they survived, they are the toughest objects in the universe. If they formed after, it means planets can grow in environments so hostile that the very idea of a stable solar system is thrown out the window. Now, let's look at the dark side of planetary science. Rogue planets. These are worlds that don't orbit any star at all. They drift through the lightless void of interstellar space completely alone. For a long time, we thought these were rare flukes, planets that were kicked out of their home systems by gravitational tug-of-war. But new surveys suggest there might be billions, if not trillions, of these wandering worlds. In fact, there might be more rogue planets in the Milky Way than there are stars. This breaks our concept of what a system is. If planets can form or exist in the deep freeze of empty space without a sun to provide energy, then our definition of habitable zones or solar systems is incredibly narrow-minded. These silent travelers are moving through the dark right now, and one of them could be passing relatively close to our own solar system, invisible because it has no light to reflect. But wait, it gets even more paradoxical. Astronomers recently found a planet orbiting a white dwarf star, the cooling ember of a sun that has already passed through its red giant phase. When a star like our sun reaches the end of its life, it expands into a red giant, swallowing its inner planets. Mercury, Venus, and likely Earth will be consumed. Then, the star sheds its outer layers and shrinks into a tiny white dwarf. You would expect the inner solar system to be a graveyard. But around the white dwarf, WD 1856 plus 064, there is a giant planet, similar to Jupiter, orbiting every 34 hours. This planet is sitting right in the zone where the star should have destroyed it. Either this planet magically survived being inside a sun, or it migrated inward from the outer reaches after the star had already shriveled up. Both theories require us to rethink the end-of-life scenarios for solar systems. It turns out, planets might be much more resilient than we ever gave them credit for. What about a planet made of diamond? This sounds like something out of a science fiction movie, but it is a real physical possibility that we've observed. Around a pulsar known as PSR J 1719-1438, there is a companion that is roughly the mass of Jupiter but so dense it must be made of crystalline carbon. This planet is likely the diamond core of a white dwarf that had its outer layers stripped away by the pulsar's gravity. It is a world where the pressure is so intense that the entire planet is essentially a singular, massive gemstone. This defies the rocky or gas binary we've lived with for so long. It shows that under the extreme conditions of the deep universe, matter can take forms that would be impossible on Earth or even on Jupiter. But back to LHS 3154b, the planet that truly cannot exist. Why are scientists so obsessed with it? because it challenges our understanding of dark matter and gravity. If small stars can hold on to massive amounts of disk material that our telescopes can't see, it means there is hidden mass in these systems. It means our calculations for the mass of the galaxy could be off by a significant margin. Or, it means that gravity doesn't work the same way in the early stages of a star's life as we think it does. We are currently using standard gravity to model these systems. But what if there is a non-linear gravity effect that happens in dense protoplanetary disks? This discovery is a smoking gun that our computer models, the very tools we use to predict the future of the universe, are fundamentally incomplete. Another impossible world is Kelt 9b. It is the hottest planet ever discovered. Its dayside temperature is over 4,300 degrees Celsius, hotter than the surface of most stars. It is so hot that molecules like water or carbon dioxide can't exist. They are ripped apart into their individual atoms. The planet even has a tail, like a comet, made of vaporized iron and magnesium. Physics tells us that at these temperatures, the planet should be evaporating away at a massive rate, and it is. But the fact that it exists at all, so close to such a massive hot star, is a testament to the planetary persistence we are starting to see everywhere. Matter wants to clump together. Matter wants to survive. Even when the laws of thermodynamics are screaming that it should be a gas cloud, it remains a planet. Then there are the Hycean worlds, planets covered entirely in a massive, deep ocean with a thick hydrogen atmosphere. We used to think you could only have Earth-like oceans or Jupiter-like gas, but Hycean worlds bridge the gap. They are impossible because, for a long time, we thought a hydrogen atmosphere would create a greenhouse effect so runaway that any ocean would boil away instantly. But new models suggest that if the planet is just the right distance away, a hydrogen can actually act as a stabilizer. This expands the habitable zone by a massive amount. Life could exist on worlds we previously wrote off as toxic gas giants. Every time we find a planet that breaks the rules, we find a new potential home for life. But what if the planet itself isn't the anomaly but its orbit? Look at HD 80606b. It has the most eccentric orbit of any known planet. It doesn't move in a circle, it moves in a long, thin needle shape. Most of the time, it is far away from its star in a deep freeze. But then, it swings around the star at incredible speeds, coming so close that its temperature jumps by over 700 degrees in just 6 hours. The thermal shock alone should shatter the planet's atmospheric stability. It is a world of seasonal extremes that would make any other climate look like a paradise. Why hasn't gravity circularized this orbit over millions of years? We don't know. It behaves like a comet but has the mass of 4 Jupiters. It is a gravitational rebel. Now, let's talk about the three-body problem in real life. We have found planets orbiting triple star systems. Imagine having 3 suns in your sky, all pulling you in different directions. Stable orbits in these systems are incredibly hard to maintain. A planet should eventually be flung out into space or pulled into one of the stars. Yet we see these worlds persisting for billions of years. GW Orionis is a system with 3 stars and a disk of dust that has been torn apart into warped, misaligned rings. There is strong evidence of a planet forming inside these broken rings. Building a world in a system where the gravitational tug-of-war is constantly shifting is like trying to build a sandcastle in the middle of a hurricane. It defies our models of quiet planetary nurseries. This leads us to the question, how many impossible planets are out there? We have only looked at a tiny fraction of the stars in our immediate neighborhood. If we are finding physics-breaking worlds 30 light-years away, what is happening in the center of the galaxy? What is happening in other galaxies? We are realizing that the standard model of our own solar system, with small rocky planets near the sun and big gas giants far away, might actually be the exception, not the rule. Our orderly system might be the weird one. The rest of the universe seems to be a wild, chaotic frontier where planets form in supernovas, survive inside red giants, and grow to massive sizes around tiny, starving stars. The James Webb Space Telescope and the upcoming Extremely Large Telescope are our new eyes into this chaos. They aren't just looking for another Earth. They are looking for the rule breakers. Every time we find a planet like LHS 3154b, we have to go back to the drawing board. We have to rewrite the code. We have to reconsider the very nature of matter and gravity. This is what makes space so exciting. It is a constant humbling of human intelligence. Every time we think we've figured out the laws of the universe, The universe shows us a diamond planet or a marshmallow world and says, try again. Think about the sheer variety of chemistry we are discovering. We've found planets where it likely rains glass, sideways, in 5,000-mile-per-hour winds. We've found planets where the air is made of vaporized rock. These aren't just different versions of Earth. They are fundamentally different expressions of physics. On a planet with 2 or 3 times the gravity of Earth, your very biology would have to be different. Your bones would need to be made of different materials, and your heart would need to be a massive pump. By studying impossible planets, we are actually studying the limits of what life itself could be. If a planet can survive a pulsar's radiation, could a form of life adapt to it too? The impossible planet LHS 3154b is a reminder that we are at the very beginning of our journey. We are like ancient cartographers who have only seen a few miles of coastline and are trying to map the whole world. We see a big fish where there should only be small ones, and we panic. But perhaps the ocean is just full of big fish. Perhaps the universe is much more efficient at creating mass than our current math allows. Maybe dark matter or dark energy plays a role in planetary formation that we haven't even begun to calculate. The hidden hand of the universe is much more active than we thought. Another fascinating impossible scenario is the mega-Earth. Kepler 10c was the first of these discovered. It is a rocky world, like Earth, but it's 17 times more massive. Before this discovery, physics told us that anything that massive should have enough gravity to pull in hydrogen and become a gas giant. A rocky world that heavy shouldn't be able to exist because it would choke on its own gravity during formation. But there it is, a solid rocky world with a surface you could theoretically stand on if you didn't mind your internal organs being crushed by the immense G-force. It defies the transition point between rocky and gaseous. It suggests that the compositional laws of the universe are more like suggestions than strict rules. And let's not forget the forbidden zone. Astronomers noticed a gap in the size of planets we were finding, the sub-Neptune desert. There was a specific size and distance from stars where no planets seemed to exist. The radiation was thought to be too intense for small planets and the gravity too weak for big ones. But recently, we started finding planets asterisk inside asterisk this desert. These forbidden planets are like pioneers in a wasteland. Every time we draw a line in the sand and say planets can't be here, we find one. It shows that the zones we create are often just reflections of our limited data, not the universe's limited creativity. So why does any of this matter to you? Because it means the universe is far more alive and far more diverse than we ever imagined. The 1% of stars like our sun are not the only places where interesting things happen. The tiny stars, the dead pulsars, and even the empty spaces between stars are all capable of hosting incredible, complex, and impossible worlds. It means that the chances of us being alone in the universe are becoming smaller every day. If planets can form in a supernova, life could potentially find a way to exist in places we previously thought were sterile. The discovery of LHS 3154b isn't just a win for the researchers at Penn State who found it. It's a win for human curiosity. It's a call to action. It tells us that we need better telescopes, better sensors, and, most importantly, more open-minded theories. We need to stop assuming that our local experience is the universal standard. We are a small planet orbiting a medium star in a quiet corner of a galaxy. Our laws of physics are based on what we see here. But as we reach further into the dark, we are finding that the high energy and high mass parts of the universe play by a completely different set of rules. Imagine what the next 10 years will bring. We might find a planet orbiting a black hole, not just in a movie, but in reality. We might find a world that is made entirely of liquid metal. We might find a system where planets orbit in the shape of a figure 8. The impossible is becoming the expected. As we tear back the curtain of the Milky Way, we are finding a spectacle that is grander, weirder, and more chaotic than any science fiction writer could have dreamt up. The impossible planet is a beacon. It's a signal telling us that the universe still has secrets that can make us feel like children again, staring up at the stars in total wonder. It's a reminder that physics isn't a holy book that is finished. It's a notebook that we are still writing in, and we just had to cross out a whole chapter and start over. That is the beauty of science. We don't fear being wrong. We celebrate it, because being wrong means we are about to learn something incredible. As you look up at the night sky tonight, find a dim, red point of light. It might be an M-dwarf star, one of trillions. And orbiting that star might be a massive, impossible giant that shouldn't be there, spinning in the dark, waiting for us to find it and rewrite our history yet again. The universe is full of rule breakers. We are just lucky enough to be the ones who get to watch them. Space is not a solved puzzle. It is a vast, unfolding mystery where every new piece of evidence changes the whole picture. LHS 3154b is one of those pieces. It doesn't fit the picture we had, so we have to build a bigger, better picture. We are moving from a world of certainty to a world of possibility. And in that transition, we are finding that the impossible is actually just a part of the completely real. Thank you for being part of this journey into the impossible today. It's a lot to wrap your head around, but that's the point. Space is supposed to be big, and it's supposed to be weird. If it were simple, we would have finished the job a long time ago. But the mystery is infinite, and so is our desire to solve it. Keep looking up, keep questioning the laws, and never let anyone tell you that something cannot exist. The universe is busy proving them wrong every single second. Stay curious, stay informed, and I'll see you in the next one as we continue to track the worlds that defy the light.